Hey, fifth graders, this is Miss Mulder. I'm going to do your math review for Wednesday, April 22nd. All right, let's look at number one. I needed you guys to round 4 and 789 thousandths to the nearest 100th. Okay, so I need to be looking, here's my 100th place, and I'm going to be looking to the right. I'm seeing that this is a number above 5, so I'm assuming this is going to bump my 8 up to 9. So I also wanted you to show it on a number line, which will be hard on the Google have but a lot of you guys are coming up with super creative ways, and I'm super proud of you. All right, so if I have 4 and 789 thousandths, my number line will only be between 4 and 7 tenths and 4 and 8 tenths, because that's where this number lives. And then I know that halfway in between there is going to be 4 and 75 hundredths, because I know that 5 always marks my halfway mark. Remember, 10 tenths make a hundredth, 10 tenths make a 1 whole, and 10 hundredths make a tenth. So it's that base 10 system. So I know if 4 and 75 is in the middle, 4 and 76 hundredths would be here, 4 and 77 hundredths would be here, 4 and 78 hundredths would be here. So now I would go really little and look at my thousandths, which would be even smaller. So I would have 10 thousandths in between my hundredths, okay? And 4 and 789 would be right here, because I've got 4 and 78, 4 and 78 1, 4 and 78 2, 4 and 78 3, 4, 5, 6, 7, 8. So I am much closer to the hundredth of the 9. So that's why when I round 4 and 789 thousandths, it would be 4 and 79 hundredths, because I am way closer to 4 and 79 hundredths than I am to 4 and 78 hundredths. Okay, that's the importance of a number line. It really illustrates how much we can make these numbers become small, 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 small. We're always breaking them up in groups of 10. Let's move on to number 2. All right, got to zoom out because I was really zooming in. Number 2, we are doing 4/8 minus 1/4. Okay, so right away I wanted to draw a model because I wanted to know what I was working with. I know that fourths can be turned into eighths. So I drew my 4/8 and I'm going to be taking away 1/4. So over here I made a model of what 1/4 looks like. I drew a square, I drew my 4 boxes, and I know that if I were to cut it into eighths, it would become 2/8. So 2/8 and 1/4 are equivalent. Over here I have 4/8, and so now I just need to subtract 2/8 from it. And what I'm left with is 2/8. Okay? If you want to do that mathematically, algorithm style, multiply that, turn it into 2/8. So now you have 4/8 minus 2/8. My denominator doesn't change. I subtract across the numerator, and I have 2/8. So the answer to that is 2/8. Moving on to number 3. I have 8 times 2/3. Well, just in my head, I know that my answer is going to be less than 8 because I'm multiplying by a fraction. And when I multiply by a fraction, I'm getting a smaller number. So if I were to just multiply it out, how we multiply fractions, I'd multiply across my numerator, and that is 16, and I'd multiply across my denominator, and that is 3. So now my job is I know that this is a fraction greater than 1, So now my job is to divide 16 by 3. 3 goes into 16 5 times. So it is 5 and 1/3. That is 8 times 2/3. Moving on to number 4. I have a rectangle, and I know that my length is 3 4/10 meters. I know that my width is double my length. Okay, so I know when I double, I'm going to double my length to find my width. So my width is 3/4 plus 3/4, or 3/4 times 3 4/10. Excuse me, 3 4/10 times 2. So that would be 6/8. Okay. Now, in order to find area, I find area by multiplying length times width. So there's my 6/8 meters. All right, 3/4 meters times 6/8 of a meter. And I'm just gonna algorithm it. I think that will be the most efficient way. So 8 times 4 is 32. I'm keeping my decimals here. I'm just gonna multiply it as if they were whole numbers. 8 times 3, let's see, is 8 times 4 is 32. 8 times 3, 24. Plus 3 is 27. 6 times 4 is 24. 6 times 3 is 18. Plus 2 makes it 20. 11. 3. 2. And I know when I multiply decimals, I've got 1, 2 decimal place values. So I go 1, 2 decimal place values, put my big fat decimal there, and I'm going to say that area is equivalent to 23 and 1200ths. Let me see if that would make sense. Well, 6 times 3 is 18, so my answer is going to be greater than 18 because I do have these little, these parts of holes here. So I'm going to check it with a calculator. I'm loving this remote learning because we can always check our work with a calculator. You can do it too. 3.3 4/10 times 6 8/10 is equivalent to 23 and 1200ths. Beautiful. Oh my goodness, I almost forgot my unit. Okay, number 5. I need to add 2/3 and 1/5. So here I set up my 2/3, right? And I already know in my head that 5 and 3 have the common denominator of 15. I can list it out, but I already am pretty certain. So I go 3, 6, 9, 12, 15. I know 5 goes into 15 because the 5 is in the ones place. 5, 10, 15. It does. It goes in 3 times. Okay, so here's my model. Here are my 2/3. I can cut it into 15ths. There we go. 5, 10, 15. Okay, so now I need to know how much am I adding into my model. I already have my 2/3, which is now 10/15ths. So I need to know what 1/5 would be as a 15th. Okay, so if I multiply my numerator and denominator by the same number, I get 3/15. So I need to add in 3/15 to my model because I'm adding. My operation is addition. So now I have 10/15, 11, 12, 13/15. I almost have one whole, pretty close to one whole. Okay, just to check that with my algorithm, times 5 times 5, 10/15 plus 3/15 is 13/15. Okay, moving on. Number 6. I need to find the area. I've been asking you guys to do this a lot because we got to work on multiplying those whole numbers. The area of a rectangle, area is length times width. This is 4 2/3. Oh my goodness, I forgot my unit. I'm just going to say it's meters. 4 2/3 meters, and this is 2 3/4 meters. It might be yards. I'm sorry, guys. I didn't put my meter or my unit. All right, so I cannot multiply whole mixed numbers. I need to turn my mixed numbers into fractions greater than 1. So here's how I do that. I turn it into a fraction greater than 1 by multiplying the denominator. I could draw a model, but this just doesn't seem efficient right now for a whole number with 4. So I multiply my denominator by the whole number, and then I add the numerator. So 4 times 3 is 12, plus 2 is 14, and I keep the same denominator. And then I multiply it by 4 times 2 is 8, plus 3 is 11, and I keep the same denominator. And now I multiply my fractions. So I multiply across the denominator. That's an easy one. 3 times 4 is 12. And then I'm going to do 14 times 10 plus 14 times 1. Make it easy. That's a quick, simple equation right there. And 14 times 1 is 14. So this is 154 twelfths. And I would say meters squared. So this can be my answer. I can say that the area equals 154 twelfths meters, or whatever the unit is, squared. I can say that's my answer. Or I can push myself a little bit further, and I can turn this fraction greater than 1 into a mixed number, because for me, I want to know how many wholes is that. I'm assuming it's going to be around 8 wholes, maybe? Let's find out. $154 divided by 12. Well, 12 goes in. No way, man. I do not have enough room to do that right there. Perfect. I'll do it right here. 154 divided by 12. 12 goes into 15 one time. 15 minus 12 is 3. Bring down that 4. 12 goes into 34. Let's see, I think it's 3. No, 2 times. Leaves me with 10. So I have 12 and 10 twelfths, because my remainder continues to be divided by my divisor. So my area is 154 twelfths meters squared, or 12 and 10 twelfths meters squared. And some of you may have broken that down into an even smaller number, like, let's see, 10 divided by 2 is 5, 12 and 5, 6. Oh, I just love math. It's like, clean it up. Make my answer really obvious. Okay, so my area can be either one of these 3, and they all equal the same thing. Thanks for joining. This POD. I learned a lesson from yesterday, and I want to use some tables with this. Okay, so we've got this teacher, and 19 students can each have 24 beads, all right? So I'm going to need, already in my mind, I know I'm going to need to multiply these, because there's 19 students, and they each are going to have 24 beads. And 12 beads are in each bag. This is a lot like that problem that we did on Monday. So if I want to know, and then she needs to know how many bags to buy. So if I need to know how many bags that she's buying, I need to know how many beads she needs in the first place. So I'm going to multiply 19 times 24, okay? And I'm going to do it in this way. I'm going to do 24 times 10, and I'm going to do 24 times 9. I like working with 10 because all I do is just pop a 0 at the end of that 24. Then 24 times 9, there's a couple ways I could do this. I could take 240 and subtract a group of 24, or I can just multiply through. 9 times 4 is 36. 9 times 2 is 18, 19, 20, 21. And now I add these two. And I get 456. So I'm going to put a big star around this, and this is how many she needs. She needs 456 beads. That's how much she needs to have so that each of her students can each have 24 beads. She only has 19 students. Wow. Okay, must be nice. All right. So I know that there's 12 beads in each bag. I'm going to set up a table. And I know that I'm going to be getting to a bigger number, but I just want to set up a table. I'm really liking this table method because it can help me get to where I need to go quickly. Watch, this is that exponential growth. So if I have bags and then I have number of beads, watch what I can do. I know one bag has 12 beads. Double that would have 24. I am nowhere near my 456, but watch how fast things grow when we double them. It's called exponential growth. So now I'm not doubling that. 2 doubled is 4. 24 doubled is 48. Still nowhere near it. Double 4. So let's see, 8, 16, 8, 96. And then if I double 8, I get 16. And when I double 96, I get 192. And then when I double 16, I get 32. And when I double 192, I get, let's see, there's 8 there, 384. See how quickly when I double that exponential growth happens? So I'm pretty close to my 456. I'm like, I'm a few away. So I'm going to slow it down a little bit. And I'm just going to go 36. So I'm adding 4. So if I'm adding 4, all I need to do is take 384 and add what 4 bags would equal, which is 48. 12, 13. So now with 36 bags, I will have 432 beads. I need 456. I'm still not quite there yet, but I need to slow it down. What if I try 2 more bags? If I go 38 plus 24, let's see, that's 6, 5, 456, bam, right on the nose. So with this strategy, I see that she needs to buy 38 bags. I'm going to make my answer very clear. There will be none left over. If one kid loses a bead, sorry kid, your bracelet's going to be a little bit wonky. But look at how I use this table. I knew that once I really started getting up there, that doubling effect happened, and I knew to slow down. And then I could just pick numbers from here and say, well, I'll add 4 to 32. And then I just had to add the number of beads that was equivalent to the amount of bags. So I'm loving this table strategy because it can get me to where I'm going quickly. I could have divided 456 by 12, but why not draw a table? Why not make it just get creative with it? Okay, so my answer is 38 bags. And there will be no leftovers, so if a kid loses a bead, they're out of